Hello, everyone. This is a talk that I gave at the OpenMolcas Symposium in Italy, Bologna, in June 2023. So my original talk had a problem with recording, so I'm using this chance to record it again, and so that my YouTube channel visitors can see it as well. So this talk is targeting essentially the audience that is not experts in quantum computing, so it will be relatively elementary, but it's assumed some knowledge of quantum chemistry. And so the idea of this talk is essentially to give a brief overview of what is current situation when it comes to using quantum computers to solve the problems of quantum chemistry. Now, you all probably heard about the Google's experiments in quantum advantage, showing that some tasks that are hard for a classical computer could be solved on the quantum computers way easier. And those tasks were not related to very useful problems. And in this talk, we're sort of interested in when quantum computing can be used to show the quantum advantage of quantum chemistry. All right, now why do we think that quantum computing can help quantum chemistry? Very naively, if you look at the electronic structure problem, without accounting for any symmetry in the second quantized form, when we work in the Fock space, our solution can be written as exponentially long linear combination of Slater determinants that are encoded by occupation numbers of our orbitals, right? And just representing that solution requires writing down the coefficients, which are exponential in number. Now, every product in this linear combination could be easily mapped to the qubits, because if you have number of qubits the same as number of your spin orbits, the occupation zeros and ones, they map very easily to qubit orientation up and down. And I hope here everyone heard about the qubits and its representation in a block sphere. Now, using such notion as entanglement, which is nothing but just a linear combination of various products when you have more than one qubit, right? Then this is the simple example where if you have two qubits, you have four linear, like essentially products of various states of those two qubits. And in the amplitudes, you can encode the information about the wave function. Naturally, if you have n qubits, you can store 2 to the n complex numbers. And that essentially shows that you can represent the solution of the original problem using quantum computers quite efficiently. Of course, this is just a representation of the solution. You also need somehow to obtain the solution. And that's what quantum algorithms do. Now, quantum computers these days are relatively small, right? And they don't have yet error correction. So we need to, if we want to bring quantum advantage sooner, choose our problems carefully so that they are useful, high utility, classically hard, and quantum easy. So the intersection of those three areas probably will give us sooner quantum advantage. Now, what do I mean by high utility, classically hard, and quantum easy? So high utility could be interpreted like in chemistry space, there are certain compounds which are more useful to develop than others. And the two simple examples would be catalysts, like the ones that are involved in the ammonia synthesis process, right? Haber process, or essentially organic light emitting diodes that we use in the screens. So all these compounds, if you can develop them more efficiently, could have a large economic impact. Now, classically hard correspond to finding the systems that are also difficult for current quantum chemistry methods, like density functional theory, for example, is very cheap computationally, but maybe inaccurate. So we would like systems where DFT will not be accurate. Also, there are methods beyond DFT, like DMRG or MRCI. So we would like to, for those systems that we are considering classical methods to be expensive if they go beyond DFT. And what quantum easy is, of course, will depend on the quantum algorithms. And in this talk, hopefully, I will be able to kind of uncover a little bit of what makes system quantum easy. Of course, that will depend on the algorithm that we use. When it comes to quantum algorithms, you probably seen this quote, which was given by Richard Feynman in 1980, that the systems that we're considering molecules, for example, they're not classical, and it's natural to use quantum systems that we can control, quantum computers, to kind of calculate molecules, right? And so this is a kind of very natural idea. So one can think of it, any quantum algorithm, as really a very simple conceptual scheme where you have question encoded in qubits, and then you have unitary transformation that transfers the question into the answer, right? And why is transformation unitary? Because processing information encoded in qubits, you don't want to lose the norm or the amount of information that you kind of put initially, right? So that's why the simplest probably way of thinking about quantum algorithms is just the unitary transformation. Now, here's the first problem. Even if you know what unitary transformation gets you from the question to the answer, still you need to figure out the way to present this quantum algorithm as a sequence of steps that the quantum computer can do. Those are U1 to UN, right? And that's not a trivial task. It's called compilation task, and it's quite hard even if you know the U. That's why, I guess, if you read the end of the quote, which started like very optimistically, that we should use quantum systems for solving quantum problems, Richard Feynman, even in 1980, sort of already realized that this problem is not that simple. Now, but to make it look relatively simple, let me tell you a little bit about like just a few algorithms that we use in quantum computing for quantum chemistry, and one simple and straightforward way to do quantum chemistry would be to use quantum phase estimation. And this algorithm, if you don't go into the circuits and don't read what computer scientists wrote about it, in a very simple physical chemistry terms, it's an algorithm which use Fourier transformation of autocorrelation function to get the spectrum. All right, so very simply, if you have any state, right, then for any eigenvalue problem in the same space, Hilbert space, you can write down the, so say, trial state as linear combination of eigenstates, because Hamiltonian has a complete spectrum of states. Then you can construct such object as autocorrelation function, which is just an overlap between the state, initial state, and the state that is evolved in time according to the Hamiltonian. And if you do Fourier transformation of that quantity, you get the essentially linear combination of delta functions that form the spectrum. Of course, no one does the Fourier transformation explicitly up to infinity, but up to finite value, the peaks will be not delta functions, but some finite with peaks, essentially. You could see the position and get the answer to the eigenvalue problem from this spectral representation, okay? Now, there are two questions arise here in this algorithm, is how to prepare initial state, psi, because you want initial state to have a large enough coefficient for the eigenstates of your interest. and then how to propagate, right? Because this is the unitary transformation that one needs to apply, but it's not so straightforward to do if you have a Hamiltonian that is complicated. So those are the two questions that will be essentially addressed in this talk. How do we do the initial state preparation, and how do we do propagation? Now, in order to do initial state preparation, there is an algorithm that is very popular these days. It's called variational quantum eigensolver. It was intended to prepare the initial state, but then later people realized that we could use variational quantum eigensolver on its own without even being a part of a quantum phase estimation, but just rather prepare a wave function and measure the energy of the state, if you can prepare a state very accurately, right? And these are the two topics I will cover in variational quantum eigensolver section. And in quantum phase estimation, we'll talk about Trotter approximation to the propagation. Now, before we start going into algorithms, let's quickly discuss how do we connect the fermionic problem to the qubits that quantum computers understand. So we start with the second quantized form of the Hamiltonian. H and G's, those are 1 electron and 2 electron integrals. They come out of classical calculations. We don't use quantum computers to calculate them. Now, they're like almost 100 years ago, Jordan and Wigner figured out how to connect fermionic operators, creation and annihilation, to qubit operators, which are Pauli and Pauli operators for individual qubits. And this form is actually quite straightforward. What x plus minus I y is just flipping the orientation of the qubit up and down, which corresponds to the change in occupation to 0 and 1. Now, what these products of z terms doing here, they are just making sure that the sign when you create or annihilate electron is properly preserved when you go to the qubits and you flip the qubits. It's important what's the parity of the previous qubits in that ordering scheme that you use will be. And what this Jordan-Wigner transformation allows you to do is isospectral mapping between the fermionic Hamiltonian and a qubit Hamiltonian now, which is a linear combination of products. So we trade one linear combination of products of terms to another linear combination of products of terms, and we can go back and forth easily. So that's quite convenient. Now we can understand what variational quantum eigensolver is doing. According to its name, it uses variational principle, and the idea is to use both quantum and classical computers to minimize the energy using some sort of trial wave function. According to variational principle, you cannot go below the ground state doing that. And what quantum computer part is doing is preparing the initial state using some unitary transformation, doing the measurement of the Hamiltonian, and getting the expectation value that then later passed to the classical computer. And the classical computer suggests another unitary transformation for quantum. This is a feedback loop that can go on and on, optimizing the unitary transformation effectively to minimize energy, right? Very simple scheme. It doesn't address, though, two questions. How do we prepare the state, right? So this unitary transformation could be done in many different ways. So what is the best way to prepare unitary transformation? Also, turns out the measurement is not trivial process, and how to do measurement is not obvious as well. Now, let's start with the state preparation. You could use your intuition how to construct the unitary transformations that gets you from the simple state to more complicated state. If you are more comfortable with fermionic representation, second quantized form, or you could use qubits and do all the manipulations there. You can easily go back and forth between those two representations using Jordan-Wigner. Eventually, everything gets to the gates, and there are some developments in the hardware efficient sort of manipulations. those I usually run into troubles that well, the parent plot also sort of issues, and so I do not recommend those. So it's usually easier to work with fermions or qubits and then use compilers to generate the gates. Now, either way, you can, for at least fermions and qubits, represent a unitary transformation as a product of unitaries, which are parameterized as exponential functions of some generators, x, which need to be just anti-Hermitian operators, right? And then the natural question then becomes is which generators to use and in what order. This is a lot like a problem of moving on some manifold, because the unitary transformations, they form a unitary group, and that is a manifold. So choosing the directions and doing the transformation in some particular order is essentially a question we want to address. And it's a lot like if you think about moving on the globe, trying to find the highest or lowest point with respect to the sea level, right? So that would be analogous, and naturally you could imagine someone would use some sort of local quantities like gradients to solve this problem. That's indeed what we're doing here. Usually we could find the gradients of energy, because energy is very natural quantity for us to optimize unitary, and this can be done, turns out to be quite efficiently on a classical computer, that you could test every particular unitary in this sequence in order to see which ones are actually having largest contribution to the energy, because some matrix elements here could be calculated relatively efficiently. All right, now using these sort of gradient-based choices, you can select the kind of the generators of your transformation, right? And in fermionic algebra, usual starting point is a Hartree-Fock state, and then the generators are single excitations, de-excitations, and then double excitations, de-excitations, and so on. In the qubit case, there are analogs of this as well, because you can build the simple product states and use the generators with the products of the Pauli operators. And that gave rise to multiple methods that are either using a particular level of excitation, de-excitation, like UCC hierarchy, or adapt methods where they select the axis based on the gradients. And in my group, we developed, say, qubit couple cluster theory, where we choose the axis also based on the energy gradients of those. Now, there are cons and pros of working in fermionic versus qubit case. The main advantage of fermionic algebra is that it's easy to conserve the symmetry at every step. And the disadvantage is that you pay in the gate cost, so essentially for conserving the symmetry at every step. And one needs to point out that potentially you don't need to kind of conserve the symmetry at every step, simply because what you are trying to get is the state that is an eigenstate of the Hamiltonian, and the Hamiltonian has a proper symmetry state. So eventually, if you follow variational ansatz or variational approach, you should be getting the state that is of proper symmetry. Now, here's some example of using this formalism for strongly correlated system, which is a stretch of the water molecule, symmetric stretch of OH bonds. So potential energy versus well, essentially the length, extent of the stretch. So we have in blue exact results, in red some mean field theory which overestimates, in pink triangles the couple cluster single and double that goes below the exact one, and in diamonds the qubit couple cluster theory. And here there are only 50 generators that you need to obtain the chemical accuracy. Now here's the comparison of 2-qubit gate count, which is the most expensive gates right now in terms of so-called fidelity in near-term quantum computing. And if you look at these small molecules and count the 2-qubit gates that you need to achieve chemical accuracy, you could see that if you use qubit couple cluster theory, the numbers are way lower than the red columns that correspond to the unitary couple cluster theory that is done in the fermionic space. Okay, now switching topic a little bit, let's talk about the measurement, because at the end, when you prepare the unitary transformation, you want to measure, and it turns out that measurement is not that simple. Turns out that more than 100 years ago, Stern and Gerlach did the experiment measuring the orientation along the z-axis, and that's exactly what current quantum computers can measure, orientation along the z-axis for individual qubits. Now, why is this a problem? Because electronic Hamiltonians contains not only z operators when you use the qubit transformation, you have x and y operators, but luckily for us, there is a sort of a resolution of identity trick that one can use. So you could put in the expectation value, the one that one obtain resolution of identity with unitaries, and rotate the system, wave function, and Hamiltonian, so that Hamiltonian contains now only the z operators in its expressions. That's great. Unfortunate problem here is that in order to find such unitary, it's equivalent to effectively diagonalizing the Hamiltonian. That's what we were trying to do in the beginning, and therefore we cannot use the solution to solve the problem. Right? Now, what do we do now? The solution actually is coming from another property of the expectation value, is that it's linear with respect to operator, and if you partition Hamiltonian into terms that are diagonalizable or rotatable into the form with only z operators, then you could do this partitioning so that the parts are easy to do, these transformations, right? All right, great. So this is the unitary circuit that one would need. And this is just an extra unitary transformation that one would require. Now, this unitary transformation needs to be simple on classical and quantum computer. And because we want to measure something without extra overhead, and we want to know what we need to measure. Now, also another kind of issue here is that when you do this extra unitary transformation, you are dealing with the parts of the Hamiltonian that is not original Hamiltonian. So the wave function that you're preparing, even if it's close to the original Hamiltonian, it may not be close to the abelian eigenstate of the part. Therefore, when you do the measurement of non-eigenstate, you will get the distribution, and the distributions could be wide or narrow. So you would prefer to have narrow distribution, then you will converge in expectation values faster. So that's another problem, to have a low number of measurements to converge faster. And so there are different ways to partition Hamiltonian for the measurement. In the qubit algebra, what one can do is to decompose into terms that contain the Pauli products that commute. Then you can measure them all together by introducing unitary transformations, which are from the Clifford group. Here's the work that explains the details. It turns out that it's easy to construct such unitary transformations. Also, it turns out that it's easy to find the groups of the commuting terms, because all the terms in the Hamiltonian can be represented as a graph where you connect the terms that commute. So that gives you a commutativity graph. And in this graph, what you need to find is subgraphs that are fully connected, right? And those subgraphs, which are called clique in the graph language, they are measurable sort of fragments. There are graph algorithms to do that, and that's what we use. Now, it turns out that you can go beyond commutativity and find the fragments which contain non-commutative terms, but you still can measure them. It turns out that we call them hard-to-fork solvable fragments. That's something that you can do in fermionic algebra. You decompose Hamiltonian into something that is solvable exactly by hard-to-fork method. And you will see in a moment why this is useful for the measurement. But let's start with a very simple idea that in order to find the Hamiltonian that is exactly solvable by hard-to-fork method, you could just start with one electron Hamiltonians, right? Because we know they all have eigenstates of the Slater determinants. And there are also orbital rotations that rotate them into the linear combination of occupation numbers multiplied by orbital energies. Now, when you go to the qubit space, the occupation numbers turn into z's, and so you can measure them. All right, great, but we need to deal with two electron Hamiltonian. And these are orbital rotations in the second quantized language. Now, in order to represent similar Hamiltonians, but in sort of one electron, two electron, or having two electron fragments, right? All you need is just substitute linear combination of occupation by quadratic form, right? So lambdas are some just constants, and these are occupation numbers again. So these Hamiltonians, they will be solved by Slater determinants in a particular orbital frame. So we use them for measurement. What the process is, we take the Hamiltonian and find the linear combination of fragments that are exactly solvable by hard-to-fork method, right? So because this linear combination gives an expression similar to the original Hamiltonian, we just optimize the coefficients through adjusting the unitaries and this lambda in the fragments so that we can recover our Hamiltonian by summing fragments. Great, let's see some results. These are measurements in millions to achieve chemical accuracy and expectation value, right? For some small molecules, right? Some numbers need to be multiplied by 110 so that they are in the scale of the plot. But there are four methods here: fermionic red and orange, and qubit methods gray and blue. Now, the difference between the bigger columns and the smaller columns is that in this bigger columns, we didn't do any specific variance optimization to reduce the number of measurements. Just whatever comes out of the method was reported. And then the next optimization can be done to reduce the number of measurements after obtaining fragments. That's the orange and the blue bars. So in general, looking at that, you can notice that fermionic methods are somewhat better, right? And interestingly, if you look at the largest molecule here, ammonia, we could say that in the best case scenario, we could reduce the number of measurements to less than 1 million, this bar. And that is a significant advantage compared to the original work, say, in this field by IBM in 2017. The methods that they used for ammonia would produce 500 million measurements. Now, to put these numbers in somewhat perspective, I should say that on the more optimistic side, if we're leaning 1 million of measurements could be done roughly in 1 minute of real time. So 500 million would be at 10 hours, and we now can do measurement in less than 1 minute. All right, now this was all about the variational quantum eigensolver that people use these days to do non-fault tolerant quantum computing without error correction. But there is a motivation to not stop at that point, but rather go to the fault-tolerant quantum computing. And the motivation is very simple, it's a necessity. If you look at the error with number of operations, let's say you are very smart about choosing the generators, preparing the wave function, measuring its energy. And so first energy error will go down, the blue part of the curve. But then the errors will accumulate and start interfering with your results. And so they accumulate actually exponentially with the number of operations. And therefore, you will lose all the advantage that you gain by quantum algorithm, unless you, of course, can correct the errors. And the second motivation for doing the fault tolerant, that the longest circuits actually can do quite miraculous things, as you will see in a moment. Like, for example, that you could not only obtain the energy as a result of the measurement, but rather find the kind of a ground state energy encoded in terms of the qubits, like zeros and ones, binary representation of the energy. That's what is happening in the quantum phase estimation algorithm. All right, returning to quantum phase estimation algorithm, we already looked at this process from the point of view of doing the Fourier transformation of autocorrelation function, and both of these operations, propagating function and doing the Fourier transformation, is a unitary, so therefore we can do them on a quantum computer relatively easily. Now, the circuits are long, but that's not the only trouble when it comes to propagating the wave function, because if you think about it, if you need to exponentiate some complicated operator, it's not easy, and there is a way to do it using, say, Trotter decomposition, Trotter theorem. This is what it is, substitute an exponent of the sum by product of exponential functions. And the question arises, like, which fragments, which HNs will you use in this decomposition? Turns out that you could use the same logic as we use in the measurement problem, because whatever you can diagonalize or bring to the Z only kind of form or Eisen form, those are the fragments that you can easily exponentiate, right? Because of this expression. So we call this Z only terms are Eisen Hamiltonian terms. And so this is what we exponentiate, or in a computer science language, sometimes these fragments are called fast forwardable. Same idea as in measurements, but the error is somewhat different in this case, because in case of measurement, it was about the number of measurements that one needs to do. Here, it's about the accuracy of the Trotter approximation, because once we kind of break things to the fragments, the question is, of course, which fragments are better, and it could be related to the Trotter error, because no one does this with the infinite k, right? So k is only finite, and the simplest example, k equals to 1, t, if it's small enough, then this approximation holds. And the question is, how good is this approximation? Different partitioning, of course, will have different errors. Here are some results on the Trotter error, which naturally is proportional to the norms of the commutators between the fragments. Again, small molecules. If we look at there are 4 algorithms again, qubit algebra in blue, greedy algorithm, and non-greedy algorithms. Greedy is generally better, as you will see here, and that's just because it's convenient. It's better for the error to have larger fragments and smaller fragments rather than uniform size, and that's what greedy provides. And also Fermionic case, the red and orange, again, non-greedy and greedy. As you can see, the greedy is generally better. Now, if you compare qubit and Fermionic fragments are better. One reason for that is simply that the molecular symmetries are preserved using the Fermionic fragments, and that allows us to reduce the norm of the commutators by reducing the space over which we calculate the norm. Now, compared to some naive Pauli product representations where we just break to the and exponentiate each Pauli, these methods give you about a 10 times reduction. With this, let me just summarize that quantum chemistry is still a very attractive area for reaching the quantum advantage, right? For that, we need to find useful systems which are classically hard and quantum easy. Now, what quantum easy is, I described few algorithms, and there you can see that not every system is the same. We will be able to look at what decompositions are better for what system, and can say that systems which are easy in terms of decompositions are quantum easy. Now, algebraic techniques are heavily used in all these Lie algebras, Clifford algebras, and groups. So these are all very useful techniques because of the non-trivial algebraic structure of the Hamiltonian. What is also important is optimization of errors and cost once you decided on a particular algebraic decomposition. And another great news that I haven't provided any results for, but the quantum algorithms we've checked so far, the quantum hardness is not correlated with classical hardness. So the systems that are classically hard, they usually are not quantum hard in terms of decompositions. So more results you can see on my YouTube channel and other videos. There's a free code in the Kilo program that we developed with my colleague Alana Spraguzik. And let me say a few words on people who did the work. So measurement problems was considered mostly by Thompson, Aditya, Seung Choi, and then Zachary. Now the state preparation is mainly covered by Robert Lang's work, Smith Patel, and more advanced algorithms like factorization is covered by Luis Martinez works and Ignacio Liza funding, and of course all of you for your attention. Thank you.